All right, in this video we're taking a look at something called moments and centers of mass. And I'm going to start with a three-dimensional problem, but that I'm going to view as if it's a one-dimensional problem. This is my lovely picture of a teeter-totter, or a seesaw that you find on children's playgrounds. Okay. And if I were to put a child here, okay. This is not, by the way, the safe way to play on a teeter-totter. You should sit on it and not stand. Okay. But if I put a child here, of course, that would cause this thing to rotate. Okay. In fact, it would rotate this way. This end would come down and this end would come up. So a moment is actually just a tendency to rotate. Okay. Now, suppose this poor child has no friends who want to play on the teeter-totter with her. So a kindly adult is going to come and play on the teeter-totter with her. This is not a good situation because, of course, this adult is going to cause the moment to be the tendency to rotate this way, because the moment caused by this adult is going to be a lot bigger than the moment caused by this child. And so we've basically created a child catapult here. So at this point, I usually ask my class, what should the adult do to make this a little bit safer for the child? And most people are able to come up with the fact that the adult needs to move in closer to the fulcrum, which is the point about which the teeter-totter can rotate. And that's because the moment is basically going to be the product of two things. It's the mass times the signed lever arm. Now the lever arm is just the distance from the point about which the rotation is going to be taken, and it's signed because there's a direction to the rotation. So I would simply attach one thing. If I said this was the positive direction, this lever arm would be positive, this lever arm here would be negative, okay? And a positive lever arm would cause things to rotate this way, and a negative lever arm is causing things to rotate that way, okay? All right, so we've got that basic idea. And now I will tell you how I wasted hours of my childhood. I would get together with a friend on the teeter-totter at school. And on the teeter-totter, you're supposed to ride it. You're supposed to be going up and down. You know, it's movement, okay? But we wouldn't try to move. We would try to inch forward and inch back so that we wouldn't move. And we could spend the entire recess trying to be on this thing that was designed to let kids move and have fun, trying not to move. We considered this fun. And then I grew up and became a math teacher. So, fortunately, those wasted hours have paid off a little bit because I now understand the notion of the center of mass. So the center of mass is just the point about which all of the mass is evenly distributed. So now we're going to switch to two-dimensional. Got this lovely lamina here. Laminas generally don't come with a clip attached, so just pretend this isn't here, okay? But the center of mass is the point so that if I were to support this at just one point, and I got my finger at exactly the right location so that it was right below the center of mass, then I could let go and it wouldn't rotate. I did not do that well because I did not correctly find the center of mass so that when I let go, the total moment was not zero and it rotated. Okay. But that's what we're going to be trying to do, is for a lamina, trying to find the center of mass. Okay. So let's suppose I have a lamina. I will just draw it as a blobular region. Okay. And I'm not going to assume that it's homogeneous. If it's homogeneous so that the mass is evenly distributed, then the center of mass would just be the literal center of the object, although sometimes that can be hard to see exactly where that's going to be. Okay. But I'm just going to say that my center of mass is some point. I'm going to call it x bar, y bar. That's the center of mass. If it were here, that would clearly indicate to us that this lamina is not a homogeneous lamina. Okay, and so I want to try to find where that thing is, and I'm going to do it one coordinate at a time. Okay. Now, if I draw the line through x bar, so that's the line x equals x bar, okay? Now, that's a little bit easier for me to work with. Trying to find the exact center of mass is a little bit tricky. But if I say, okay, I'm going to try to find the x-coordinate of the center of mass. So I'm supporting the lamina on some sort of a knife edge like so. That way, this support cancels out any tendency to rotate this way. So the only possible rotation would be this way. Now, obviously, if I put my arm here, we have such a rotation. But if I put my arm here, we don't have such a rotation. So I've correctly located where x bar is. And then I could do the same thing for y bar. I would simply support the lamina on a knife edge that was going this way till I found where it didn't rotate. And then the intersection of that horizontal and vertical line are going to be the center of mass. But I want to try to find it. Okay. Now, when I actually have the lamina, I can, just sort of do it by trial and error. If I just have a description of it, I'm going to need to try to figure out how to find that. And so we're going to do that by our usual 4-step process. So the first thing we're going to do is we're going to chop. We will chop the lamina up into a bunch of little pieces. And I don't know what x bar is, so what I'm going to do is I'm going to try to find the moment, or the tendency to rotate, about the line x equals a. So I'm just going to say for an arbitrary line x equals a, let me see if I can find the tendency to rotate about that line. For some lines, that's going to be positive, meaning that things would rotate this way. For some lines, that's going to be negative, meaning it wants to rotate this way. When I find the right one, that moment will be 0. If I can find the line x equals a, that about which the moment is 0, then I will have found that a value will be x bar. That will be the x coordinate for my center of mass. Okay. All right. So I have chopped this up into little pieces. Now I'm going to approximate the tendency of each little piece to rotate here. So let's say we're looking at this piece right here. I'm going to choose a representative point. If this is the ijth rectangle, I'm going to have, let me actually draw it over here. I'm going to pick some point that I'll call Pij star, which is just Xij star, Yij star. Okay. So to calculate the moment, I need the mass of this thing, and I need the lever arm, both of which are changing, but I've gotten really good at denial. So I'm going to say the mass, and then, actually, let me do lever arm times mass. So for the lever arm, I'll simply take my x value and subtract a. And notice that's going to give me something that is signed if, as I've drawn it here, my x value is to the right of the line x equals a, x minus a will give me something positive. But when I'm working with something over here, x minus a will give me something negative. Okay. All right, and then for the mass, well, if this isn't homogeneous, I don't have a density, just a constant density, but I have a density function. So I can take rho evaluated at my representative point times the area. So the density function, which is mass per area, times area. So this is approximating the mass. This is approximating the lever arm. This video has actually been going for a little while, so I'm going to stop the video here and pick up with step 3 in the next video just to keep it from getting too long. Okay, see you soon.